So briefly, pulse oximetry is simply measuring the difference in the light that is emitted by an LED and that which is detector on the other side of a piece of tissue. It utilizes Beer's law of doing so. And Beer's law, we know, helps us to describe the amount of light that's absorbed by a tissue. It simply states that the amount of light absorbed is proportional to a concentration of that substance, the absorption coefficient of that substance, and the length of that substance that light needs to pass through for any given amount of that tissue. Now, the two substances that are of concern for pulse oximetry are oxygenated and deoxygenated hemoglobin. Now, each of these two substances have very different absorption coefficients, particularly at different wavelengths of light. A pulse oximeter essentially transmits two wavelengths. One wavelength at 660 nanometers, which is in the red spectrum, and another wavelength at about 940 nanometers, which is the near infrared spectrum. Now, deoxygenated blood has a very high absorption coefficient at 660 nanometers, that which is about the red spectrum. And an oxygenated hemoglobin has actually a very low absorption coefficient at the same wavelength. In contrast, the flip side is true at 940 nanometers. So oxygenated hemoglobin absorbs quite a bit of light at 940 nanometers, while deoxygenated blood does just the opposite. So if our pulse oximeter sends light of both of these wavelengths through a piece of tissue, that is both 660 nanometers and 940 nanometers, and we only see light come through the other side of that tissue at 660 nanometers, then we know that all the light from that 940 nanometers was absorbed as it was going across that tissue. Now, what that tells us is it was probably absorbed because there was a high concentration of oxygenated hemoglobin present to absorb that particular spectrum of light. It also tells us that there was not much deoxygenated hemoglobin in that tissue to absorb the light at 660 nanometers. So from that information, we can calculate a ratio of the amount of oxygenated versus deoxygenated hemoglobin in that tissue sample. Now, that ratio we refer to as the saturation percentage of oxygen, or oxygen saturation percentage, SpO2, which you see displayed on these units. Now, the two wavelengths of light passing from the LED to the detector are passing through a variety of tissue outside of just blood. That includes collagen, fat, bone, and fingernail, in the case of the pulse oximeter that's attached to the finger. Now, each of these tissues has its own physical properties, has its own absorption coefficients, and has its own tendency to scatter light. This would normally interfere too dramatically with the pulse oximeter reading to give us meaningful results. To compensate for this, what we do is look at the dynamic portion of that absorption. That is only that portion which is changing over time. So we subtract the lowest absorption from the highest absorption over a defined period of time, knowing that the only thing that's going to change in that finger during that period of time is the amount of blood flowing through it.